In this video, I want to derive the inverse Laplace transform of this function here, a function of s, where s is the complex variable. And I want to do so by using the straight definition of the inverse Laplace transform. So in particular, I want to calculate it by using a certain complex integral, and the integral starts at sigma, and I will describe more in detail what sigma is. This is a real number minus I infinity to sigma plus I infinity. Then we have the function 6s squared plus 8 divided by s squared plus 4 squared. And then I have e to the st ds, and we have to divide this by 2 pi I. Now let's sketch the zeros of this denominator in the complex plane. So let's assume that this is the complex plane. We have the real part equal to 0 here, where we have a pole. We have a pole because you can see that s equal to 0 makes this denominator 0. So this is actually a pole, and the multiplicity of this pole, mult, is equal to 2 because it's squared. So we have 2 of such zeros of the denominator. So we have 2 of such poles. Then we have other poles due to this part of the denominator, in particular here for s equal to 2i, and here for s equal to minus 2i. And the multiplicity of these two poles is also equal to 2. That's quite easy to see. Now, when we take the inverse transform, we have to integrate over a line which is vertical. And you can see it from here. So we are integrating from sigma minus I infinity. So this means that this is equal to sigma. The real part of this distance here from this y-axis, if you want, is sigma. And sigma, you have to be careful because sigma must be greater than the real part of these zeros, of these poles here. So the real part of them is 0. So it means that the real part of s, or in this case sigma, must be greater than 0. And why is that? Well, this is not so difficult to understand. It has to do with some convergence reasons, but in particular, when we integrate over this integral here, we will show quite soon that we can close this contour, so we can make a contour out of this vertical line, and the result of the integral will be the same. So if we close the contour, we will still have the same result. And in particular, we can resort to the residue theorem to calculate this integral here, because the integral over this part of the contour, which we can call capital gamma, we can show that that's 0. So if we integrate over this capital gamma, we obtain 0. So basically, the integral is equal to this. So only this vertical line gives us a non-zero contribution. But if we close the contour, this is an advantage for us because we can use the residue theorem, right? In particular, we have these 3 residues here. These are the 3 poles that we have to consider. Now, if we choose sigma less than 0, for example, it is quite easy to understand that we have something like this. We can close the contour like this, and we have nothing inside the contour. So it's as if we can use the residue theorem, and we can say, okay, the result is equal to 0, but that's not the correct result. I will not get into more technical details here, but when we invert this function, we will not get 0. So we have to consider contours with the vertical lines that are on the right of this y-axis to, let's say, to surround these poles. And now at this point, we can resort to the residue theorem, and we can say, okay, so if we call this function f of s, this would be equal to 2 pi I, and then we have another factor of 2 pi I, so we have to divide by 2 pi I, so we get 1. And then we have the residue of the function f of s evaluated at s equal to 0 plus the residue of the function f of s evaluated at s equal to 2i plus the residue of the function evaluated at s equal to minus 2i. So we have to calculate these three residues. And before doing that, let's quickly show, or at least let's try to understand why the integral over this gamma is 0. That's not difficult to understand, because now let's remind ourselves that this this r, I mean the radius of this semi-circumference that I'm considering, capital R, goes to infinity. So in particular, if we consider, for example, this angle here between the origin, between this line that's coming out of the origin and it's connecting this point, which is the origin itself, where we have the pole, one of the poles, with this point, then the angle between that line and this vertical line here, this angle will tend to 0. And similarly also for this angle here between this line and this part of the vertical line. So this angle here would tend to 0 when r goes to infinity. Now, if we consider this part of the function f of s, in particular this exponential, when we move around the circumference, the variable s will be equal to sigma plus e, or in particular r, e to the I theta, right? Because basically we are considering a certain point, for example here. We can describe this point by using this vector, and this vector is given by a sum of two vectors. So we have for example this line, or this vector, and then this vector here. So this vector is r e to the I theta, whereas this vector here is sigma. So you have sigma plus r e to the I theta. Now let me clean my picture a little bit, because otherwise it's quite difficult to understand, because it's getting dirtier and dirtier. So here I have e to the I theta. But anyway, you can see that if I substitute this s here, we have e to the sigma t times e to the r e to the I theta times t, right? So we have something like this. Now let's focus on this. We have e to the r cosine theta t times e to the I r sine theta t. This is just an oscillating term, and this part will go to 0 if the cosine of theta is negative, because remember that r goes to infinity, so this would be the prevailing term, and sigma is positive, but it is finite. It's greater than 0, but it is finite. R goes to infinity, and the cosine of theta, what happens to the cosine of theta? Well, as we move from this point in this manner, so counterclockwise to this point here, we are moving basically from the angle pi over 2 to the angle 3 over 2 pi. So the angle theta should lie in this range, because remember that this point is moving up because r is going to infinity. So you can understand that the angle between the vertical line and this line here is going to get smaller and smaller as r increases. So we are moving from pi over 2, because we have to consider the angle that's formed. So theta is the angle between the real line, so this line here, so it is measured from here, and then we are moving like this, so this is theta, right? So if we are here at this point, in particular, if we are moving, if we are considering r greater and greater, so bigger and bigger, and it is in the limit approaching infinity, theta is going to pi over 2. And similarly for this point here, we are going to 3 over 2 pi, or 3 pi over 2. So this means that the cosine of theta is negative, right, in this interval here. So it means that this will go to 0. And it is quite intuitive that the integral, the result of the integral over there is also going to 0. So that's going to 0, and therefore we can only consider the integral over this line. But now that we have closed the contour, we can integrate, oh sorry, we can sum the residues that are contained inside the contour, and we have 3 residues. How do you calculate those residues? Well, there is some theory behind it. In particular, we can expand a function by using a Laurent series, and the coefficient c sub minus 1 is the coefficient that we have to calculate for the residues. In particular, c sub minus 1 is the residue of the function evaluated at a certain point s equal to s0. Now, in complex calculus, there is a formula for this residue. I will give you the formula. I have already proved it in another occasion, but here I'm using the formula, so I have 1 over the multiplicity minus 1 factorial, and then I have the derivative m minus 1 ds to the m minus 1, and then I have s minus s0, so s0 is one of the poles. We will see that s0 can take the values 0, plus 2i, and minus 2i, and then I have to raise this to the power m, and then I have f of s, and I have to evaluate this at s equal to s0. Now, for example, when s0 is equal to 0, the first pole, we have c sub minus 1 equal to, remember that in our case, the multiplicity is equal to 2, so we have the derivative with respect to s, so this factorial would be equal to 1 because we have 1 factorial there, 2 minus 1, which is 1 factorial. And then here I have s minus s0, but s0 is equal to 0, so we have s to the power 2, because we have m there. And then we have f of s, which is 6s squared plus 8 divided by s squared plus 4 squared, e to the st. And then we have to evaluate this at s equal to 0 after we compute the derivative. So we can see that this s squared simplifies. And now this is just up to a calculation of a derivative. It is quite trivial, it is quite mechanic, it's easy to calculate. I will not do it here. If you calculate this, you will get a simple result, t over 2. Similarly, we can calculate c sub minus 1 when s0 is equal to 2i, and this is equal to the derivative with respect to s of s minus 2i, because in this case s0 is 2i, squared 6s squared plus 8 divided by s squared plus 4 squared, e to the st, and then we have to evaluate this at s equal to 2i. So if you do this calculation, you get minus 1 over 4 e to the 2it times t, and similarly s0 equal to minus 2i. Well, this is actually quite easy to understand, that the result here will simply be the same as this one but complex conjugated. So I will write it down, but it's quite intuitive what we are going to get here, because this is just the complex conjugate of this, d over ds, and then I have s plus 2i squared, 6s squared plus 8 divided by s squared plus 4 squared, e to the st, s equal to minus 2i. So we have to calculate it at s equal to minus 2i. And the result is, of course, minus 1 over 4 e to the minus 2it times t. So at the end of the day, what we get is this. We get that the inverse Laplace transform of 6s squared plus 8 divided by s squared plus 4 squared This is just equal to the sum of the residues that we have up there. So we have t over 2, and then I have, now we can factor out minus 1/2 times t, and then I have e to the 2it plus e to the minus 2it divided by 2. This is just the cosine of 2t. So we can factor out t over 2, or if you want just t, and then I have 1 minus cosine of 2t divided by 2. And if you want, you can simplify this further, because this is equal to the sine squared of half this angle, so sine squared of t. So the final result is t sine squared of t.